Yeah, good morning, students. Good morning to the 25th lecture of fluid mechanics. So, in the last class, we have discussed about the problems and the pipe bend equation, and also the problems related to the pipe bend equations, and also the momentum equation derivation. So, in this class, we'll start the various applications of momentum of equation. So where we are using the momentum of equation in a real-time applications, So here we'll see the various things where the momentum of equation is used in the fluid mechanics, in various sectors, like where the fluid is flowing at a very high speed, right? Where the fluid is flowing at a very high speed on a planed surface, curved surface, inclination surface, on a reaction of a jet, right? Yes. Yeah. So if you see the topic, application of momentum equation. So whatever the momentum of equation we have derived in the initial classes, Q is equals to momentum of equation AV. So here we'll see the real-time applications where we are having the momentum of equation applications, right? Yes. Yes. So the first one is the impact of jet on a plane surface. Impact of jet on plane surface. So whenever the water is flowing through a pipe with a high velocity, so that is nothing but the impact of jet. So here the jet is on falling on the plane surface. The jet is falling on the plane surface. Next, second application is force due to the flow. Force due to the flow around the curved vein. Force due to the flow around the curved vein. So here vein is nothing but a surface which is in a curved shape. So the second one is the force due to the flow around the curved vein. So in this force due to the jet around the curved vein means the vein is also a plane surface which is in a curved shape. So the curved vein. So these are the devices where you can see on a Kaplan turbine, Francis turbine, or any some sort of pumps, where you can see in the next semester subject, that is the hydraulics machines. Third one is the force due to the flow of fluid around the pipe band. So which this is the thing what you have already discussed in the last class, the derivation of the pipe band. Then the fourth application is the reaction of the jet. So how the reaction of a fluid flowing jet takes place whenever you are using the applications, right? Yes. Now see the force exerted by a jet striking a flat plate. So if you see the first application, the impact of jet on a plane surface. So ఈ application ని మనము various planes ద్వారా we will see in a real time how the process goes. Now see here. So from this figure you can say the plate comma normal to the jet. So this one is the hatched portion is a plate. So this one is a plate. This one is a plate. This one is a plate. So where whenever you are perpendicularly forcing high stream of water falling on this jet, how the velocity, how the see the direction of the water, how it is striking this one and moving in this direction, moving in this direction, water jet, right? When you see the plate is making at an angle, the plate is making at an angle, that is acute angle. So see the velocity of the flow, thereby it is also making an angle, it is also making an angle. Then how the jet of flow is at right side, is at left side. So when the angle plate is making an angle 90 minus V. Now see here, consider a jet striking a flat plate that may be perpendicular or inclined to the direction of the jet. For example, take a pipe, water pipe, and flush it. Keep your hand, right hand, straight perpendicular to the left hand water pipe. Then flush the water onto the right hand palm. That is how then see the movement of the water flowing in the from your right hand side, right hand plate. So when your right hand acting as a plate, making an angle upwards or downwards, now see the same direction of velocity of flow pumping onto the plate. So whenever you are making an angle towards upside, how the water is exiting outside. Whenever you are making downside angle, how the water is flowing, right? So this is an example you can directly do with your hand. Now, the plate may be moving in the initial direction of the jet. So here from this figure what you are taken, here in initial case, the plate is perpendicularly straight. Here the plate is making at an angle, Again the assumption is the plate may be moving. So ఈ రైట్ హ్యాండ్ మీరు ఇట్లనే పట్టుకొని లెఫ్ట్ హ్యాండ్ ద్వారా పైప్ ద్వారా వాటర్ ఫ్లష్ చేస్తూ స్టేషనరీగా పెట్టి చూడండి. తర్వాత రైట్ హ్యాండ్ని టువర్డ్స్ ద పైప్, away from the pipe, towards the pipe, away from the pipe, or making an inclination towards the pipe, away from the pipe. Then you can see the differences, how the reaction takes place, how the water is flowing, how the velocity it is striking onto the moving plate, initial direction of the jet. Next, third one, it is helpful to consider the components of velocity. So this type of experiment, striking on a flat plate, it may be a perpendicular or inclined, moving or stationary. It is helpful to consider the components of velocity and force, vectors perpendicular and parallel to the surface of the plate, right? Perpendicular and parallel to the surface of the plate. Next. Next one. The general term of a jet velocity component normal to the plate can be written as. So generally, the jet velocity of a component normal to the plate can be written as. See here, if you are taking a plate with an angle, so this is a x-axis, is a normal surface where the jet is striking onto the inclined plate. So whenever it is making inclined, so you are having the velocity. So the velocity of a jet. So V normal is equals to V minus U. V normal is equals to V minus U cos theta, by because it is making an angle. If you are making a triangle with this one, so triangle with this one, so if it is making an angle theta, we are taking the adjacent side by hypotenuse, that is V minus U cos theta. Next, the mass flow entering the control volume. So the mass flow entering into the controlled volume is equals to, this is the thing what we have already derived in the initial class. M is equals to rho into A, V. Then what is V here? V normal. V normal is equals to V minus U. So rho into A into V normal, that is equal to V minus U. Now when the plate is stationary, momentum is equals to, mass is equals to rho into A into V. So when the plate is stationary, what is the equation you have to write? M is equals to rho into A into V. Thus the rate of change of momentum normal to the plate is equals to, rate of change of momentum is equals to rho into A V minus U of V minus U cos theta. So what is the thing, why you have written two cases here? So generally applying this one, M is equals to rho into A V minus U into this V normal. What is the V normal? V minus U cos theta. So that is the thing they have written for the change change of momentum normal to the plate. Whenever there is a change of momentum, that is equals to rho into a v minus u of v minus u cos theta. Then after simplifying this one, we are getting rho into a v square minus v square cos theta, v square cos theta, if the plate is stationary and inclined. So when the plate is stationary, and making an incline to the normal, when it is stationary and making incline to the normal, the formula rate of change of momentum is equals to rho a square v square cos theta. If the plate is both stationary and perpendicular, so if the plate stationary ga undi perpendicular ga ante straight ga undi anukondi, then what is the formula you have to write? Rate of change of momentum is equals to rho into a v square. So because akka theta manaku undadu, theta is 0, there is no angle, that's why we are writing rho into a v square, right? So this is the thing we are generally seeing in the velocity of jet striking on any flat surface. It may be horizontal, sorry, it may be vertical, or it may be inclined surface, Next. Now, the force exerted normal to the plate, the rate of change of momentum normal to the plate is equals to force exerted normal to the plate is equals to rho into a v minus u cos theta. That as you can see at this point, right? Now, there will be an equal and opposite reaction force exerted on the jet by the plate. So what happens whenever the jet is falling on the plate? There will be equal and also opposite reaction. There will be equal and opposite reaction force exerted on the plate. Next one. In the direction parallel to the plate, the force exerted will depend on what? The force exerted depend on the shear stresses. In the direction parallel to the plate, the force exerted will depend on the shear stresses between the fluid and the surface of the plate. So whenever it is acting parallel to the plate, whenever the water is acting parallel to the plate, the force exerted will be depend upon the shear stresses between the fluid and the surface plate. So in the initial classes we have discussed, the water is flowing in a layers. So when this water is touching any boundary of any plate, it may be a closed or open, what happens? The shear stresses are acting on this water or a fluid. Next, for ideal fluid, there would be no shear stress and hence no force parallel to the plate. So generally ideal fluids undavu. So if there exists an ideal fluid, so what is the condition? There would be no shear stresses forming and no parallel to the plates are existing. Next, if you see an example of this jet of plate moving or inclined, so what is the thing? A flat plate is struck normally by the jet of water. A flat plate is struck normally by the jet of water 50 mm in the diameter. So what is the diameter of the pipe? The diameter of the pipe is 50 mm, right? So it is striking a flat plate with a velocity of 18 meters per second. So what is the velocity? 18 meters per second. Now what to calculate? Calculate the force on the plate when it is stationary. So calculate the force on the plate. When the plate is stationary. Second one, the force on the plate when it moves in same direction as the jet with a velocity of 6 meters per second. So first case when the force on the plate is stationary. Second case here when the velocity of water is moving at 18 velocity of water is moving at 18 meters per second. Here the plate is also moving at what speed? 6 meters per second it is moving. So these are the two conditions. Now draw the diagram. The velocity of jet moving in the opposite direction, V. So this is a stationary plate which is faced towards the front of the water jet. Now, if you see in the two cases, of example 2, a jet of water from a fixed nozzle has a diameter of 25 mm and strikes the flat plate at an angle of 30 degrees to the normal to the plate. So initially plate ఇలా ఉంటే it is making an angle of 30 degrees. It is making an angle of 30 degrees లోపలికి తీసుకోవాలి, not this side. You have to make an angle 30 degrees. So what is the diameter of the nozzle here? The diameter of the nozzle is 25 mm. Next, the velocity of jet V, the velocity of jet and the 5 meters per second. The velocity of jet is 5 meters per second. And the surface of plate can be assumed to be frictionless. So the surface plate of friction is frictionless. Then what is the thing you have to calculate? Calculate the force exerted normal to the plate. So normal to force, general force exerted normal to the plate. If the plate is stationary and if the plate is moving with a velocity 2 meters per second in the direction of the jet. So ఇక్కడ jet velocity ఎంత ఉంది? Jet velocity is 5 meters per second, right? In this direction the jet velocity is 2 meters per second. Now, so in the example 1 we have seen the plate is perpendicular to the water flow. In the example 2 we have seen the plate is making an angle 30 degrees to the water flow, right? So these are the two cases for the above application where you are using the force exerted by the striking flat plate, right? Now see the derivation for the answers for that. For each case of control volume is fixed, the relative fixed related to the plate. So for each of the case, the control volume అనేది ఏంటి? The control volume of water is fixed చెప్పేస్తాం. So in both example 1 and example 2, what we have seen means, example 1 లో the plate is fixed. In example 2, the plate is not fixed, right? So here what happens? Here in the both cases we are using the fluid for a constant volume. We are using constant volume fluid. Since we wish to find out the normal to the plate, the in the x direction is chosen perpendicular to the surface of the plate. So we wish to find the force exerted normal to the plate. When the force is exerting normal to the plate, the x direction is chosen perpendicular to the surface of the plate. Now the force exerted by the fluid on the plate in x direction is given as force exerted in x direction force is equals to Fr plus Fb plus Fp, right? So that is equals to m mass of velocity output minus velocity input in the x direction. Then what it can be written as the resultant force R is equals to minus Fr, okay, minus Fr, that is equals to Fb plus Fp minus m of V out minus V into the x direction. So in the initial class, before class we have said it is a negative direction, so that is in the minus Fr. So the gravity force, the body force Fb is negligible, and if the fluid in the jet, the body force is negligible and the fluid in the jet is assumed to the atmospheric pressure throughout, the Fp is taken as 0, the pressure force is taken as 0. Therefore, how to write the resultant? R is equals to Fp is taken as 0, Fb is negligible, therefore R is equals to minus Fr, that is equals to m of V out minus V in, that is equals to m of V in. So ఇది చూసినప్పుడు converting this positive negative, V in minus V out x in the x direction, where m is a mass per unit time of fluid entering the control volume. So control volume lo the mass m per unit is flowing. Then V out and V in are the measured were relative to the control volume, which is fixed relative to the plate, right? 14, 50, yeah, 20. So see the first one, the first case example 1, it is a stationary plate. We'll solve this one. Yes. Yes. So if the plate is stationary, the mass per unit time is equals to mass per unit time leaving the nozzle. So mass per unit time entering the nozzle is equals to mass per unit time leaving the nozzle, that is equals to rho into A into B. Now the initial component of velocity related to the plate in x direction is stationary perpendicular ఉన్నప్పుడు V cos theta, making an angle is V cos theta. when the final component of velocity related to the plate in x direction is 0. Now what is the relative? What is the total thing? R in x direction, the resultant is equals to m of v in minus v out. In x direction, that is equals to rho of AV, this one, rho of AV into v cos theta, rho of AV into v cos theta, that is equals to rho of a v square cos theta, rho of a v square cos theta. So now substituting values, Rx is equals to 1000, rho is equals to 1000, A area is equals to pi by 4, 25. So converting into meters, that is 0.25 square into velocity is v square into angle is 30 degrees. This is the thing you are getting, right? So when it is making an angle of 30 degrees, converting this at 30 degrees, the resultant force, the resultant is 10.63 Newton. 10.63 Newton. Next. The second application is force due to the deflection of jet by a curved vane. So whenever you are taking another plate instead of a flat plate, if you are taking a curved plate, what are the forces acting on the curved plate when a curved plate is stationary or moving, making an angle with respect to the x direction or not making an angle with respect to the x direction? Now we'll see this application. Okay, now both the velocity and momentum are vector quantities. So here what it is saying, both the velocity and the vector moments are in a vector quantity. Each if the magnitude, even if the magnitude of the velocity remains unchanged, even if the magnitude of the velocity remains unchanged, the change in the direction of the stream of fluid will give rise to the change in the momentum. Now, if the stream is deflected by the curved vane, so the stream is deflected by which vane? Not a plane, it's a curved vane entering and leaving the tangentially without impact. A force will be exerted between the fluid and the surface of the vane to cause a change in momentum. So momentum eppudu vastundi change. So whenever the force of liquid is flowing from the one end to the other end of the vane, touching the surface of the vane, thereby there is a change in the momentum. So see here, so if this is the black portion is the curved vane, so the water is flowing along the surface of the curved vane, so thereby the surface of the layers of the liquid are touching the boundary of a curved vane, thereby the change in the momentum occurs. Now from this figure you can see, the section 1,1 entering in the section 1,1, leaving in the section 2,2. So u1 is the initial velocity, u2 is the final velocity. Now with respect to the axis, it is making an angle theta. Now this is traveling next direction, flowing in the y direction, the legend, right? Now it is usually convenient to calculate the components of this force. It is usually convenient to calculate the components of this force parallel and perpendicular to the section of the incoming stream. So this can be used as a parallel or perpendicular to the incoming section of the stream. The resultant can be combined. So how the resultant will be? The resultant will be combined to give the magnitude of the resultant force, right? The resultant can be combined. So both the parallel and perpendicular will be combined to give the magnitude of the resultant force which the vanes exert on the fluid, and equal and opposite reaction of the fluid on the curve, on the vane, right? Now if you see the important points, the pressure force is 0 as the pressure at the both inlet and outlet are atmospheric. So what about the pressure in this vane? So these are open to the atmosphere. The pressure force is 0 at inlet section and also at the outlet section. Next one, no body forces are acting in the x direction. So no body forces are acting in the x direction, only in the y direction. So in the x direction, because of the curved vane shape, there is no body forces acting in the x direction. But in the y direction, there is a body force acting weight of the fluid. So what happens in the y direction? In the y direction, the body force is acting downwards, gravity. So thereby there is a body force acting in the y direction. Therefore, this is often small. This is often small to the jet volume is small and sometimes ignored in the analysis. So during the analysis of this vein, so because of the jet volume, because of the often jet volume is small, so therefore it is taken as negligible. Next, third one is force exerted on bends and closed conducts. Force exerted on pipe bends and closed conducts. So here the force will act on the bend pipe due to enduku force acting on the bend pipe. Now see the figure here. So this is section 1-1, this is section 2-2. Here the area of a pipe, here the area of pipe is separate. Here the initial velocity u1, the initial velocity, final velocity u2. Here the rho1 and the rho2. So you are making the axis, it is making to the normal some angle. Now the fluid changes in its direction. So why it is making the forces are acting on the pipe at bend section? The fluid changes its direction. Okay, the fluid energy changes its direction. Initially it is going like this, so suddenly it is taking a curve like this, or initially it is going like this and suddenly it is making a bend, and suddenly it is moving like this, and suddenly it is going in this direction. So like this, what happens? The fluid changes its direction, thereby the force will act on the pipe bend. Next, if the pipe tapers, there is a change in the velocity magnitude. Automatically, whenever you are having a constant pipe like this, so diameter అనేది equal గా ఉందనుకోండి, so there is no change in the velocity magnitude. Whenever there is a change like this, so there are changes in, whenever there is a change like this, small diameter to big diameter. So see this one, this is a big diameter, this one is a small diameter. Thereby you are getting a change in the velocity magnitude. Next point, do not forget the pressure forces. So whenever the water is pumped into the pipe bed with some force, one should not forget the pressure forces. Right? Then why do you want to know the forces acting in the pipe bed? This force can be very large in the case of water supply line pipes. So generally, whenever the water is flowing in a closed conducts such as the pipes, the force is very large. The force is very large in case of water supply pipelines. Next, if the bend is not fixed, it will move and eventually break the joints. So what happens whenever you are having a joint, whenever you are having a pipe connection like this? So whenever you are having a pipe connection like this, so this is a joint. So this joint అనుకుందాం, right? So this is a pipe 1, this one is a pipe 2. ఈ రెండిటికి మధ్యలో you are having a joint. So whenever this joint is not formed fixedly, then what happens? It will have some leakages and eventually break the joints. Next one, we need to know how much force a support must withstand. So we have to consider other things like how much amount of force is acting on the pipe bed in order to withstand the forces or pressure acting on the pipe. Yes. Next, fourth example is reaction of a jet. Whenever the momentum of a stream of fluid increased in a given direction, so whenever the fluid is flowing in a pipe, in what direction, either in x direction or in y direction, whenever the fluid increases its direction, whenever the fluid is increased, what happens from one section to other section? There must be a net force acting on the fluid in that direction, right? So whenever it is increasing, what happens? Automatically there will be a total force acting on the pipe. That is, a total force is nothing but the net force acting on the pipe in that direction. Next, by using the Newton's third law, what is the third law? It is saying that there will be equal and opposite force exerted on the fluid on the system, right? So by using the Newton's third law, which is the equal and opposite force exerted by the fluid on the system, this reaction of jet can be done. Now, if we take an example of a reaction of a jet, if we take the example of reaction of a jet, reaction of a jet, see the examples. The first example is force on a nozzle at the outlet of the pipe. So whenever you are having a pipe inlet and outlet, so you have to see the force acting at the outlet of the pipe. Anything holding the nozzle, example fireman, must be strong enough to withstand the forces. So if you see the example fireman and other, so where you can heard the name fireman. So here the fireman can be stated whenever you are having any fire accidents, you are having firefighting equipment. So whenever the firefighting equipment comes, persons comes, the police comes, they will open the nozzle and they will strike the jet of water. So at that point of time, the outlet velocity can give the example of the reaction of the jet. How does it react? What is the reaction of the jet at that point of time to withstand the forces? Next one, the reactive forces exerted when the fluid is discharged in the form of high velocity jet. The reaction force exerted when the fluid is discharged in the form of high velocity jet. So what are the examples of this statement? The aircraft, rocket motors, etc. So whenever the relative force exerted when the fluid is discharged in the form of high velocity, ఎక్కడ జరుగుతుంది ఈ situation in the aircraft applications, in the rocket motors applications. Understood? Yes. Next one, how to convert the Euler's equation of momentum along a straight line. Euler's equation of motion along a straight line. Right? So this is a topic we'll discuss now. So already you know the Euler's equation. So how it is acting moving along a straight streamline. So take a figure, consider a figure where you are having different cross section area, right? So the initial stage A, B, and the final stage is C, D. Final stage is CD. Yeah. So if you see in the initial case, you are having the area change, EV velocity and pressure, and the outer stage A plus change in the area plus change in the area, velocity change in the velocity, plus pressure change in the pressure. Now see the total length. The total length of the pipe is dou T. Total length is dou T, and the pressure is acting on the closed pipe. Now see the datum line. See the datum line of the pipe Z from the ground line. See here. So if this is a reference line, datum line, the reference plane. So the datum line from A is Z. The datum line from D is Z plus delta Z. Right? So these are the pressure forces acting in all directions for the pipe. So this is a total length is dot T. So here the force is acting perpendicularly downwards automatically. Now with this axis, it is making an angle theta. Now see, it is an equation shows that relationship between the velocity, pressure, elevation, density along the streamline. So what is the equation is showing here? The equation gives the representation or relation between the area, the velocity, the pressure, the elevation, and the density along the straight line, right? The mass per unit time of flowing, is equals to rho into A into velocity, that is already known. Next, the rate of increase of momentum from AB to CD. So what's happening here? The rate of increase of momentum from AB నుంచి AB, this is a AB, from section 1 or AB to section 2 to CD in the direction of the motion is equal to rho of AB, taking common rho of AB, group change in the velocity v plus dou v minus v, So after simplifying this one, what's the value you are getting? Rho into A into V dou V. Rho into A into V dou V. So this is a change in the momentum from A to B. This is the change in momentum from A to B, right? Yes. Next, the force acting to produce this increase, the force acting to produce this increase of momentum in the direction of motion can be detained as the force due to the P. The force due to P in the direction of motion is equals to P into area. The force due to pressure, change in the pressure in opposite direction is equals to P plus dou P into A plus change in the area. Right? Change in the pressure into change in the area. That is P plus dou P plus A plus dou A. Now, the force due to the pressure side producing a component in the direction of motion is equals to P into rho into A. Now, the force due to the mg producing a component opposite motion, mg cos v is equals to the resultant force in the direction of motion is equals to Pa minus of P plus dou P, A plus dou A plus P side dou A minus mg cos v, mg cos v. Now, what is the P side? That is equals to P plus K into dou P. What is the K? K is a constant or a fraction. Now, the mg is equals to rho g, that is a volume. Mg is a volume, that implies rho g of A plus 0.5 dou A into delta S. Whereas cos V is equals to delta Z, dou Z by dou S, dou Z by dou S. Now, neglecting the small quantities, so what are those? The resultant force is equals to minus A dou P minus rho G A dou Z. Applying the Newton's second law, what's happening here? So, applying the Newton's second law, rho into A into V into dou V is equals to minus A into dou P minus rho G A into dou Z. Now, dividing by rho A into dou S, that is equals to 1 by, so after getting this one, now take a differentiation, that is 1 by rho dou P by dou S plus V of dou U by dou V by dou S plus G dou Z by dou S is equals to 0. Now, in this limit for delta S is taken as 0, that is equals to 1 by P dou P by dou S plus V of dou V by dou S plus G of dou Z D of dz by ds is equals to 0. So after taking this one into consideration, so this equation can be written as in this equation. So what is this equation? Now we are calling them as Euler's equation. Euler's equation. This is a Euler's equation. So giving the differential form, the relationship between the velocity v, the pressure p, and the elevation z, and the density rho along the streamline for the steady flow can be written as ఇది ఎలా రాస్తున్నాం 1 by P dou P by dou S plus V of dou V by dou S plus Z of dou Z by dou S is equals to 0, right? Okay. Now, for incompressible flow, rho is equals to constant. Then the integration of the above equation along the streamline with respect to S can be written as, so the constant in with respect to the S, that is equals to P by rho plus V square dV ante V square, dV means V square by 2 plus the G into Z. So differentiation with the respect to S, we are having P by rho plus V square by 2 plus Z GZ, that is equal to constant. Now, the terms representing energy per unit mass, now dividing by G, we are having rho P by rho G plus V square by 2G plus అక్కడ G ఉంది కాబట్టి G cancel అవుతుంది. So we are getting Z, that is equal to constant, that is equal to H. Now this is nothing but the Bernoullis equation. So what it is having? It is having a pressure energy plus kinetic energy plus datum energy, in which the terms represent the energy per unit weight. Now, the Bernoullis equation states that the relationship between the velocity v, pressure P, and the elevation z for steady flow of friction fluid is constant density. So, the Bernoullis equation can be written as pressure energy plus velocity, kinetic energy plus z is equal to constant is this one. Now, the alternative for this one is P plus half rho v square plus rho g z is equal to constant, in which the terms represent the energy per unit volume. energy per unit volume. The Bernoullis equation can be written along a streamline between 1 and 2 points can be written as, say, రెండు equate చేస్తే 1 and 2 for solving the problems. Rho 1 by rho g plus b1 square by 2g plus z1 is equals to p2 by rho g plus v2 square plus by 2g plus z2. So with this velocity changes in section 1 and section 2, we have already solved some problems, right? So like this, the Euler's equation can be converted into the Bernoullis equation, right? The Euler's equation can be derived by differentiating, so you are getting the Bernoullis equation. So these are used for solving the problems, right? So hope you understood the applications of momentum equation. So what are the 4 applications, right? We are using the reaction object, pipe, stationary plate, curved vane, and the pipe bends, and also the Euler's formula, right? So with this we'll stop the class. The time is up, right? So I will share this video in the YouTube. Once the YouTube is uploaded, I will share the link to your group. So view it and like it and share this link to other students, those who are not in the class. Thanks for listening patiently.